Hello, in this video we're going to talk about an introduction to additive manufacturing. So what is additive manufacturing? Well, let's break that term down. In its simplest sense, additive manufacturing is a manufacturing technology suite which allows us to selectively add material on top of itself. So rather than the traditional subtractive method where we start with a big block and we slowly chip away through machine cutters or other tools and techniques to end up with our final part, in additive manufacturing we start from a substrate, sometimes a part, sometimes from nothing, and we will selectively add material where we need it. So additive manufacturing is a manufacturing process where we add material on top of itself. You could think of it as micro welding, you could think of it in that type of mentality. Okay, so now we've broken down the term additive manufacturing, let's think about what the 7 main additive manufacturing technologies are. So as per the American Society of Testing of Materials definitions, there are 7 core technologies. Those technologies are on the screen now. So within the 7 technologies, we are looking at a variety of polymer and metallic technologies. At AMS and within the AMA, we focus very heavily on metallic technologies. The remainder of this video will also focus on one of those metal technologies in particular, but more of that later. So on the screen, as you can see, there are images to depict the 7 main technologies, a description of the feedstock type, the source of energy which allows the material to be fused on top of it, and also an AM readiness level as per AMS's perception. What we can see is that there are a relatively widespread of technologies where the energy is either added directly in terms of some form of laser or electron beam, but also where there are liquids, binders, or direct feeds. So now let's go through and have a look at these technologies individually. So first up, let's look at binder jetting. In the case of binder jetting, we have a powder and a binder or liquid. The powder is applied in a single layer before the binder is therefore applied directly through some form of nozzle, not a million miles different to a traditional ink printer. That binder is selectively applied so that the material which is to be bound is therefore connected with this binder, this fluid. The energy source therefore can be heat and sometimes can be ultraviolet rays to cure the binder. That allows us to create a part which is connected together with a form of glue, and that can also have additional processes like post-process sintering, which would allow the binder to be fully reacted to the materials which are being joined together. In the case of binder jetting, AMS will give this technology an AM readiness level of 3. Binder jetting shows great promise. The mass market of additive manufacturing technology seems to be most likely to be penetrated from binder jetting. That's because it was envisaged that this technology will be able to produce parts very quick, cost effective, and therefore compete with mass produced castings. It would also be envisageable that binder jetting would be able to access markets like the automotive market, which some other additive manufacturing technologies would be unable to penetrate just due to the costs and economies of scale. So now let's move on to the next technology. Direct energy deposition is exactly as it says in the tin. The energy source is directly deposited at the point of need. Direct energy deposition, or DED for short, will use powder or wire. And interestingly, as you can see in the image, we've split to show 2 different types of technology. On the left-hand side of the image, we can see a kinetic version. Now in this instance, what we're looking for is for our feedstock, which is normally a powder, to be deformed in a solid state. Solid state means the powder does not melt. So whatever properties, whatever material chemistry, whatever grain is only ever going to be plastically deformed as it connects to the substrate or connects to the parent material underneath it. It's a very interesting technology and an interesting method in which you can guarantee chemical composition compatibility. In the case of direct energy deposition, or DED, with a powder or wire and a laser beam or an electron beam, we are looking at a full remelt. So in these instances, the material is added at the source of the energy, electron or laser beam. The material is fully melted and solidified rapidly. In terms of readiness level, AMS perceives this technology as somewhere between 2 and 4. It's a very interesting range for us here. The kinetic or solid state DED process is normally known as cold spray. Though in the term cold spray you would assume the powder is cold, it actually gets quite hot. It is shot at supersonic speeds towards the substrate. The technology itself is a little bit immature in terms of material availability and material readiness levels, which has pulled it down in our rankings. However, in the cases of conflict, in particular the problems with the Ukraine and Russia, what we have seen is cold spray is a very good deployable solution and has had significant impact, we are understanding. Many cold spray machines are expected to have been live producing parts for the Ukrainian war effort. So for this instance, I think it's only fair to assume the cold spray process would be a very high AM readiness level, but maybe a slightly lower material readiness level for other industrial verticals, like aerospace and space, for example. In the case of wire and powder DED processes where we use laser or electron beams, the readiness level is very high. These parts have already made it into service in aerospace and space, and the technology is only held back from being a fire in our minds just because of the availability of future materials being limited to very high impact space companies like NASA, SpaceX, etc. DED is a process that shows great promise for very large parts, and it's imperative for additive manufacturing success that we continue to push the development of DED. Next, we have material extrusion. In this case, material extrusion may also look quite familiar to any other technologies that you've maybe seen in schools, colleges, or even for sale in supermarkets these days. Material extrusion uses a plastic wire going through a heated nozzle and is often called FDM, Fused Deposition Modeling, or sometimes FFF. These technologies are all using polymer wires through a heated nozzle to create a malleable process where the deposit of plastic wire is selectively added in the shape made by the extrusion head. The AM readiness level is a 5 here because this technology exists everywhere, from schools to aircraft parts. Fused Deposition Modeling, or FFF, has had a say in many parts across prototypes, tooling, and production parts. The material availability in the case of material extrusion is normally limited to polymers. Those polymers are often PLA or ABS, and in the top end are sometimes PEEKs or PEX or variants of. Future developments in material extrusion are focusing on the materials in particular. Engineering materials, very high performing polymers, but also bound polymers where we maybe have a metallic or a ceramic component in the matrix, which is then used in a sintered post-process, allows us to make ceramic or ceramic infused at least, and sometimes relatively dense metal parts using this relatively low cost and accessible process. Material extrusion is one of the most cost-effective methods of getting into additive manufacturing, and it's entirely plausible that you could be purchasing a machine and having it operating the same day for less than £100. At the top end of material extrusion, the machines are still several £100,000 and are used in aerospace standards. It's a very adaptable technology. Next up is material jetting. Material jetting has a lot in common with binder jet, where we still have some form of ink or liquid which is deposited. The difference in this instance is, rather than binding onto a standard powder bed, in this instance we jet the material where we need it. It removes the need for a surrounding powder bed, it removes the need for depowdering, and is a very, very interesting process for mass producing polymer parts in particular. This ink or liquid is cured via UV light and allows the part to become relatively solid very quickly. Material jetting has great impact in the future of polymer large production and is a very adaptable process that allows you to compete quite consistently with injection molding. For those reasons, AMS has given the AM readiness level of 5 for material jetting. Next up is powder bed fusion. Powder bed fusion for us is the most mature of all of these processes. And the reason for that is because this is the single technology we have the most development experience with, we've pushed the boundaries of the most, and have the highest capability in. In powder bed fusion, a powder bed, very similar to as we discussed in binder jetting, is used. That powder bed is selectively melted, and in some cases the laser beam, which is often the energy source, is called a selective laser melting process. Within powder bed fusion, we use a laser or electron beam as the energy source. those laser or electron beams are used to fuse or melt the powder together. In some of the earlier days of powder bed fusion, we actually only ever sintered the materials together. And in those technologies, it's still used today, but it's a polymer process, not necessarily a metals process. In a modern powder bed fusion machine, we more often than not will expect to see metal powders added, and they will be fully melted and solidified and reconnected together. The additive manufacturing process of powder bed fusion with metals is often called selective laser melting. Selective laser melting is a really good definition because we selectively melt using a laser beam. So when we are creating our parts, we select where the laser melts as per all of the other additive technologies, but also what's really important here is we do have a full melt process. That gives us issues. The issues with full remelt is that we are then having a melt pool. And in the case of a melt pool, similar to DED technologies, the ability of the material to resist the absorption of oxygen, nitrogen, hydrogen, or other nasties that are there and present in the technologies, it becomes much more problematic to prevent. Laser powder bed fusion or electron beam melting have both been used readily in space, aerospace, land, sea, marine, and they will continue to push the boundaries of the additive manufacturing technologies' maturity and impact on industrial verticals across the world. In the case of metal powder bed fusion, we use a variety of different sizes powder. We also have a variety of different alloys available that we can use. Ample development is currently underway to develop new materials, novel processes, novel methods in which we use these laser electron beams. The development in laser powder bed fusion more recently has focused on larger machines with more lasers. At AMS, we have a machine with a single laser, which does more than what we need with our 280 by 280 millimeter platform. But in some instances now, there are multi-meter machines with hundreds of lasers available to produce parts. Mass producing parts in powder bed fusion is not normally cost effective, and therefore it is quite often used up to around 5,000 to 10,000 units. Because of the impact powder bed fusion has had on so many industrial verticals, that for us was a no-brainer to give an AMS AM readiness level of 5. Next up is sheet lamination. In the case of sheet lamination, rather than a powder bed, we selectively melt areas of a sheet which is laid on top of each other. In some of the earlier days of additive manufacturing in the late 80s and early 90s, this seemed to be one of the highest productivity-based metal technologies available. This lamination technology has been used in other forms in not quite an additive sense before, so therefore the adoption of an additive manufacturing variant seemed logical. Due to the lack of current use of sheet lamination, we have given an AMS AM readiness level of just 2. There doesn't seem to be any current developments in sheet lamination to our understanding. Next up is VAT photopolymerization. In the case of VAT photopolymerization, we use a resin or a liquid which is cured by a laser beam or a light source. Interestingly, VAT photopolymerization was the first patented and commercially available additive manufacturing technology in the mid-80s. That longevity as a technology is what has given it an AMS AM readiness level of 5, alongside the fact that it has been used in production parts all over the world for many years. The benefit of having a liquid bed rather than a powder bed is you can have a much more accurate and very nice finish to all of your parts. This technology has been used extensively in wind tunnel testing across space, aerospace and motorsport for many years and continues to be used as the #1 technology to create wind tunnel models. Most of the development with VAT photopolymerization in recent years has come to the source of energy. In the earlier days, it was a laser beam, and more recently, digital light and LEDs have been used to cure this resin bed. That has allowed VAT photopolymerization to go from being a very high cost, industrial grade technology to being available for several £100s for entry level users. The feedstock type of a resin or a liquid hasn't stopped there being additional developments. The benefit of using a resin is that we can engineer them, we can develop them. An extensive development of those materials existed for many years. We also can add binders and add additions to these resins. It's not uncommon to find ceramic inclusions in resins which are used to create very stiff, high quality resin-based parts. They don't have the same UV degradation, they have a much stronger and more consistent performance, and that stiffness allows them to be a really good model in the wind tunnels in particular, because the stiffness can replicate that of carbon fibre parts, often found on aerospace and motorsport components. And that concludes our overview of the 7 core AM technologies. So for the rest of this video, we're going to really explore additive manufacturing in laser powder bed fusion. So using a powder bed process, it's really important for us to get close to the machine. So let's get over there now. So here we are in front of our laser powder bed fusion technology. This is our SLM Solutions SLM 280. So let's first have a look at the architecture and the infrastructure that's needed before we even think about how the additive manufacturing process of powder bed fusion works. So firstly, over to my right, you can see the instigation of compressed air. We have to make sure compressed air is fed into the machine for its safe operation. The compressed air is fed through a dryer before it's fed into the machine to keep the laser system cool. There's also a separate water chiller to aid this process. Now if you come back to me, what we'll start to do is look at a little bit more of the infrastructure of the machine. So at the very top of the machine we can see where powder is handed into the machine in this top mount. And then we have the main build chamber volume, and then also the PC where all the sort of system controls are held. So if you come in, let's have a look inside the build volume. So in the build volume, this is where the magic really happens. What we have is a camera system in the top of the build volume, which allows us to take photographs before and after all of the remelt. We also have the main laser system. The laser system is protected by a glass, and that's where the laser will then fire down onto our powder bed. Well, the powder bed can only get there with the recoater. The recoater is shown at the back, which is a dosing unit with the words SLM Solutions written along the front. With the build plate in the machine and the build plate height set based on the thickness of the layers we want to produce. So for example, that could be 30, 40, potentially 60 microns. So likely around half the width of a human hair. The doser collects powder and then will coat forward and backwards to put a single layer of powder. The laser will then selectively melt the areas that we want to turn into solid before the recoater returns over for another layer, another layer, another layer, continually dropping by the same layer thickness. We then will potentially process thousands of layers before we end up with our three-dimensional part. We will then remove all of the surplus powder from the build chamber, normally using our cyclonic separator, to be left with the final part that we wanted to produce. That's the fundamentals of the powder bed fusion process within our SLM 280. Now let's zoom back out and have a look at how do we handle the powders in the system. So right there was the fundamentals of the laser powder bed fusion process. The powder is really key. So we mentioned already how the powder is fed into the system. What we also need to be able to ensure we understand is how do we handle the powders. Powders in the additive manufacturing process will often change. I always describe them as the dynamic part of a fixed process. So to make sure that we stop any of these changes from having an adverse effect on our parts, we normally make sure we sieve to remove all the very large and the very small particles. Come with me to have a look at our sieve capability. In front of us here is our Russell Finex and Pros Collide sieve. This for us is the method in which we control our powders. Powders are fed in through the top and we use a vibration mechanism to vibrate the powders through a sieve. We collect all the good powders at the bottom and the not so good powders, the large powders that have evolved or devolved through the process, are captured on the right hand side. This sieve allows us to keep consistent powder size in our process. Consistent powder size in our process will give us a more consistent melt, and a more consistent melt gives us consistent parts and make sure we have happy customers. There's now one final critical factor to talk about for our laser powder bed fusion machine, so let's get back in front of the machine. The final piece of this puzzle is to make sure that that melt is really well controlled. To control the good melt, the final piece of the puzzle, as well as the powder in the laser system, is the gas flow. The gas flow will always flow across the bed. And what we're really trying to do is remove spatter, remove other fumes that come from this micro welding process. The gas flow will keep all of the atmosphere inert and will stop any oxygen absorption into the melt. That allows us to have really tight control of the mechanical properties of our end part, and it is a key factor that makes laser powder bed fusion a high precision, high performing technology. Thanks for listening.